Hi, I'm Mike Seaman with Eta Power. In this video, part 2 of a two-part series, we'll measure the efficiency and loop gain of a synchronous buck converter and compare those results with those produced in Eta Designer. In part 1, we created a synchronous buck converter in Eta Designer, modeled after the TPS40170 evaluation module from Texas Instruments. We defined the power components and specified the controller compensation network. In this video, we'll take the circuit and verify its efficiency and loop stability against the EVM board. Let's start by measuring the efficiency of the EVM. This is our EVM board. We have the input supply connected on the left, and the power converter with its two MOSFETs and power inductor is here, controlled by the TPS40170 controller IC here. We've already replaced the MOSFETs with the Fairchild parts to achieve higher efficiency, as shown in the first video. The output load is connected on the right. We're also using the test points on the EVM to connect the voltage sense lines. Now, let's look at the measurement hookup. To measure input current, we measure the voltage across the 5 milliohm shunt resistor. The output current is likewise measured across this 2 milliohm shunt resistor. We're measuring the input and output voltage directly on the EVM through these Kelvin connections. This method ensures we measure the efficiency of the converter without including the cable or connector loss. We're using the 60 volt 3.5 amp power supply as the input. The output is this 120 volt 30 amp electronic load. At each data point, we are adjusting the input supply and output load to the desired value. The two shunt voltages and the input and output voltage are measured by this data logger. The data logger will automatically transfer the measurements to the computer for logging. The advantage of using a data logger rather than multimeters is that the same front-end circuitry can be used for each channel. Thus, any relative errors between the measurements are canceled out, resulting in a more accurate efficiency calculation. We'll start by opening the Fluke data logger program. We've set up 4 measurement channels. The first channel is set to 150 volts and is our input voltage. The next channel is set to the minimum range and measures the input current across a 5 milliohm shunt resistor. The third channel is set to 30 volts and measures the output voltage. Finally, the fourth channel measures the output current across the 2 milliohm output shunt resistor. We'll now configure the output files and start the logging. We'll set the data logger to capture every 20 seconds, which will provide enough time for us to adjust the line and load conditions and for the output to stabilize. We can now start the data logger and begin the test. I'll skip through all the data acquisition. Okay, now we've spent about half an hour capturing nearly 100 data points. We can now stop the data logger and examine the data. I'll open the CSV file and save it as an Excel file to add our plots. Here's the raw data captured by the data logger. I'll start by deleting the irrelevant columns. I'll label the columns. And then I'll add the shunt resistor values. I've previously measured the shunt values by passing an identical current through both shunts and measuring the voltages from the data logger. The ratio between these voltages can precisely determine the ratio of resistor values. With these shunt values, we can make columns to represent the input and output currents of the converter. We'll set them to be the shunt voltage divided by the shunt resistance. Finally, we'll add another column with the converter efficiency by dividing output power by input power. Let's format it as a percentage with a few extra decimal points, and then fill down. Okay, now let's add a plot for efficiency data. We'll start by selecting the first series at an input voltage of 10 volts. We'll now choose a scatter plot, which will plot the efficiency versus load current. Let's go and format the axes as desired and add horizontal and vertical axis labels. Now we'll add additional data series for the other input voltage ranges. We'll start by labeling the existing series as 10 volts, and then add our 12 volt data. We'll proceed by adding the data series for the remaining input voltages. Alright, here's our efficiency data. We'll add a legend to indicate the input voltages. We can quickly look at the data. Down here, we see a bit of a bump due to the zero voltage switching action of the converter at light loads. Now, let's compare this data to the efficiency predicted in Eta Designer. We'll start Eta Designer and open the buck converter we've created in the first video. We'll run the sweep efficiency simulation to quickly generate the efficiency over the low current and line voltage range. These ranges mirror the data points we've taken. The curves look very similar to our experimental results. However, we should overlay the points to see how close they actually are. We'll start by exporting this efficiency data as a CSV file by choosing Export Data from the File menu. Okay, now we'll import this CSV file into our Excel spreadsheet. Here's the exported data from Eta Designer. The input voltage is across the x-axis, and the load current is across the y-axis here. Let's copy this data into a tab in our spreadsheet. And now we'll reformat the data to appear in one column, which will make it easier to plot. We'll add our VIN values to a new column on the left. I'll go ahead and finish moving the data over. We need to add another column to contain the efficiency as a percentage. Now we'll copy the efficiency plot we've already made and add the simulated points. We'll add all the simulated points as one series to make things easier now. We'll select the output current for our X data and the new efficiency column as the Y data. Now the only thing left to do is reformat the series to get rid of the line and to make the experimental data more visible. Alright, here you see that we have a very good match between the simulated and experimental values. The high current values match extremely closely, allowing you to use Eta Designer to estimate thermal performance and worst-case efficiency of the design. At light loads, there's a slight error in the efficiency data. As Eta Designer is using datasheet values to model the losses in the converter, there can be minor discrepancies between the results from Eta Designer and what can be seen on the bench. Actual components may differ slightly from the datasheet properties, and variations also exist between individual components. Finally, error can creep up when the modeled circuit does not match what is built. Eta Designer contains a Monte Carlo tool to help you understand how component variation can affect efficiency, stability, and other converter metrics. Eta Designer tries its best to ensure that accurate, quick efficiency results are available to the user. However, these efficiency simulations are only a prediction, not a substitute, for bench efficiency results from a physical prototype. Our next task is to compare the stability, represented by the loop gain, between Eta Designer and our EVM on the bench. In Eta Designer, we'll start by looking at the operating conditions for which we'll measure the loop gain. These are the typical values of the design variables of the converter. Here, we'll use an input voltage of 24 volts and an output current of 5 amps. Now, we'll view the loop gain by choosing Loop Gain from the Simulate menu. The loop gain is shown in red. It has a crossover frequency, or bandwidth, of 34 kHz and a phase margin of 52 degrees at crossover. The gain margin is not shown as the phase does not cross -180 degrees in this frequency range. Eta Designer's Bode plot stops at half the switching frequency due to the Nyquist sampling criterion and the Bode plot algorithm. Now let's look at how to measure this loop response on the bench. Here's our power converter. For this measurement, we're using the Digilent Analog Discovery 2 data acquisition unit. Please watch our other video called Measuring Power Converter Loop Gain using the Analog Discovery 2 for more information on this method. We have the waveform generator in the Analog Discovery 2 connected to the isolation transformer. This transformer will isolate the signal while reducing its amplitude by about a factor of 2. The output of the isolation transformer is fed into a 50 ohm resistor inserted between the output voltage node and the feedback network. This connection will inject a varying disturbance into the feedback network. Next, we'll look at the data acquisition channels. There are 2 channels, each with 12-bit, 100 megasample per second analog to digital converters. We will hook channel 1 up to the feedback network side of the converter to measure the input to the feedback network. Channel 2 will connect to the output of the converter. Thus, the difference between channel 2 and channel 1 will represent the loop gain of the converter. Now, I'll open the Digilent Waveform software and choose the Network Analyzer module. I'll start the sweep at 100 Hz, ending at 1 MHz, with 500 samples. We'll then set the generator amplitude to 100 millivolts, using 20 milliseconds and at least 16 periods to let the converter settle after each frequency change. I'll set the desired range to start at 50 dB with a range of 100 dB. Make sure the converter is operating at the desired line voltage and low current, and then press single to run the sweep. The waveform software iterates through the sample points, collecting the loop gain. The data collection has finished, and the loop gain is shown in blue. Let's compare the waveforms by placing the measured results on the left and the Eta Designer simulation on the right. The waveforms look fairly similar. Let's first look at the crossover frequency. Our gain crosses 0 dB at 33.8 kHz or so, identical to the value in Eta Designer. Our measured phase margin is 57.5 degrees, close to the 52 degrees in Eta Designer. Let's look at when the phase crosses 0 degrees. This happens at 162 kHz, similar to the simulation. We see a lot of noise beyond half the switching frequency, which is expected in a loop gain measurement. Eta Designer doesn't include these frequencies, as the gain and phase have little meaning. Finally, let's look at the primary LC resonance. In the data, this happens at 8 kHz, which is nearly identical to what the simulation predicts. The peakiness of the LC resonance differs between the two simulations, as a constant current load is used on the bench, while a resistive load is used in the simulation. For a voltage mode buck converter like this one, the crossover and phase margins are strongly dependent on the parasitics of the inductor and output capacitors. As these are often not modeled very accurately in the datasheet, there may be some small errors in the simulated results, as we've seen here. As always, Eta Designer is best used as a prediction tool and not as a substitute for measuring performance on the bench. In this two-part video series, we've seen how easy it is to model a real converter in Eta Designer. After modeling the converter, we can predict its efficiency and control stability very accurately and verify the results on the bench. I hope you've enjoyed this video and have learned how to use Eta Designer to estimate the performance and stability of a power converter. These predictive tools can help you quickly and accurately design your power converters and reduce prototyping iterations. Please check us out at etadesigner.com to download a trial version and to view more videos like this one. Thanks.